I have my first slide. Actually, I made my slides last night, so I'm going to modify my talk based upon the previous two talks. It's on a completely different space. So I wanted to talk about before there was data. So all of my talk is about data, how to use data. And I started working in compilers way before there was actually data. So if anybody who has worked in compilers would know that we are king of rules, or we are queens of rules. Basically, we write a lot of rules to generate code, right? That's how compiler systems work. So when I did my undergraduate dissertation, it was about code generators. So you got M languages, N machines. You would write M times N compilers. Instead of that, how do you write N plus N compilers? So that was kind of the idea. I wrote my dissertation, so it was filled with words like code generators. And the person who was reviewing my dissertation said, one mistake I see through your dissertation is you write generator one too many times. Instead of saying code generators, you're saying generator. I don't understand it. Later on, I worked in program generators where how can you automatically generate programs without actually having to write them? So I write translators from one language to another, and we would write giant rules files. So the first project I worked on was converting modular to C++. And there was modular grammar, there was C++ grammar, and you write these giant transformer rules, and they automate this code. And that was also, pretty fascinating at that point of time. People who bought those things did not believe that, you could write those things. They didn't look like human-written code, right? They were computer-generated code. Then I went on to work on search and some other things, e-commerce. Then I came back to work for a compiler team. Nothing has changed. So the compilers work pretty much the same way today as they worked 20, 30 years ago. So they're giant systems where there are lots of analyzer rules that are written, and then you've got complex programs that process those. But the world has changed. We have a lot of data. So that's where I want to start my talk. We have tons of data, and what do we do about them? So for example, we got about 19 million software developers in the world, according to, this is 2013, probably a lot more now. And if you look at 10 years of GitHub data, when you analyze that, you find there are 10 million users, 26 million projects, 400 million commits, 7 million committers, about 1 million active users per month, and so on. So there's tons of data. And if you look at a company like Microsoft, internally, we have a ton of code data. So what can we do with this? What can we learn from this? What can we use these to automatically generate or help developers be more efficient? So that's kind of the goal of what we are trying to do. So, if you look at this is from the Forrester research. So it talks about software development cycle. So it says software development cycle, you've got ideation phase, basically you got analysis, planning, etc. Then you got development. So when the users are developing code, they need assistance. IntelliSense is one of the things I'm going to talk about. But there's a lot of things that can automatically be done. You can run analyzers which will tell you, hey, change the variable name from this to that so that the code is more readable. Or you've initialized a variable, but you're not using it. Maybe you want to kind of throw away that code. So there are tons of assistance today available. If we use Visual Studio family of products, you will see that there are about 200 analyzers that run while you are editing the code. And these are all written, there are giant rules behind them that actually drive those analyzers. Then you're actually doing a compile and a build system. So when you're trying to do the build, you want to say what parts of the code are risky, what part of the code you need to test, right? We don't have testers anymore. So before, when you run testers, you automatically generate tests. But usually you try to run those tests that cover, path coverage was one of the things we look at, which is, does it cover all parts of your code? So do you want to test all parts of your code? But if you have an analysis of the code, if 50% of your code doesn't get executed, why even test that part, right? So that's kind of what we want to do today if we have data available, right? And then finally, what can we do in terms of deployment and reiteration of that? So what can we do there to decrease the defects when you deploy your code? Can we use AI to do that? So there's a lot of, in every phase of software development, there's data available, and we can use that data to say, can we improve this phase of software development using AI. So that's kind of the overall goal of what we do there. And I'm going to give you a couple of examples of how we do that. So, and with this data we have, large-scale AI algorithms. Now, the previous speakers talked about all the advances in the AI algorithms, but we are in a different space. We are in the space of code, and code looks very different from human-typed language, human-typed text, right? But we have distributed systems, we have the cloud, and we have the GPUs. So we can use all of these things to revolutionize developer productivity. So that's kind of what I want to talk about. So let's start with data. So one of the things we do is, because we have so much data, let's first look at what the data tells us before we kind of throw some algorithm at it. And that is very useful. And we are not in research teams, we are in product team, which is when I go with an idea to a product manager or with my product peer, they're going to say, well, does it work? Is my user going to use it? Because the user is editing code. If there's an AI system that comes and interferes with that process of developing code, they're not going to accept it. So it's got to provide the SLA that the developer accepts. So going back in 1971, analyzed 800 Fortran programs and looked at all the loops in Fortran programs. And he found that 95% of the loops having indexes that increment by 1. Right? And he said that 85% of the loops have 5 statements or less. 53% of the loops are singly nested. And this is good insight into what kind of code people write, right? And if you look at more recent analysis, my colleagues at Microsoft Research, they analyzed 25 million lines of code, and they found very similar statistics. 95% of the code has less than 15 lines. Of the loops are less than 15 lines long, right? 90% of them have no nesting at all, and they're very simple control structures. And 50 classes of loop idioms cover about 50% of concrete loops. Now, these are very good insights if you want to do any kinds of AI-driven analysis you want to write against you, right? So what are the benefits of this? You can have data-driven frameworks for code refactoring. You can even have new paradigms for programming languages, because if most people write code like this, why not optimize those kinds of codes, right? So you've got huge opportunities in language design. So how do we represent code? So we saw in the first talk, what do we do with human languages? But programs are interesting, right? They have structure. So you got syntax, you got very, very synthetic syntax, you got functions, and you got statements, and you got control structures, and you got loop structures, etc., etc. But at the same time, if you want to automatically generate them, then you could, in some sense, you have more structure than you have in human languages, where there's a lot of looseness. But on the other hand, this structure is highly restrictive. And the structure is only syntactic. Beyond syntactic structures, you got semantic structures. And beyond semantic structures, the intent of writing this code. So now if you want to automatically write algorithms against this, you got to do a bunch of stuff. So there are 3 ways of representing code. So one is the standard lexical code generative models, like using tokenizers that's used in NLP systems, right? So you got n-gram models like using NLP. Your sequence-to-sequence models like RNNs and LSTMs you can use, which is kind of what we use today a lot, right? And what we found in our analysis is neural models are way superior to n-gram models. Not surprising there. But on the other hand, because the code structures are complex, they are a lot more expensive to train and a lot more expensive to execute and need a lot more data. So if I want to build an AI system that is like edit time AI system, it is going to not provide the kind of SLA that's required to do it in real time, right? But on the other hand, if you do offline analysis, these perform much better than just simple NLP n-gram models, right? Now, more recently, there's a ton of work based upon word2vec. We call what is called code2vec or code to sequence, how to represent programs as sequences and then do analysis on top of it. And that's kind of what we tend to use a lot, right? Then there is some work using abstract syntax trees. So abstract syntax trees are very standard in the compiler world. Any program that you write gets converted to syntax trees, and that gets analyzed. So that provides you better representation of your code than sequence models. But at the same time, they're a lot more expensive to process. So there is some work using LSTMs over abstract syntax tree on representation for doing limited synthesis of programs, meaning limited auto-generation of code, not a lot. And finally, we have got the latent model, which are much harder to do. So if you look at a piece of code, what are the hidden design patterns in that code? What are the programming idioms that were used inside the code? What are the standardized APIs that are used? So if you look at any code, there will be typically you make API calls, and there are sequences of API calls that you use, and what are the idioms that are used in the sequences of calls? Can we represent them in some efficient ways, and can we learn from them? So there is in the programming language world, there is something called tree substitution grammars, which is we can use that to identify similar grammar productions, and then we can do machine learning on top of that. So these are 3 different areas of work where researchers in programming languages combine AI to automatically generate program or automatically generate program fragments. So what are the opportunities we have in terms of using these models in the software development world? So the simplest thing is the recommender system. So if you go to Amazon or eBay, you buy something, and then what is the next thing that you should buy? Or if you look at the NLP world, what is the next word you're going to type? Or what is the next sentence that you're going to type? And so on. In this case, what is the next piece of code that you're going to write? So if you're a programmer, you're typing code in, what is the next piece of code that you're going to write? And a prediction model for that. So that's kind of what we are interested in doing. And so instead of, if you look at IDEs today, right, if you're making a function call, if you say string dot, it'll give you an alphabetical list of functions to call. And if your string class has 200 methods, then, and you're using the 159th method, then you have to scroll all the way down to find that method. That's quite intrusive. So can we do something better than that? And that's one of the examples I'm going to give in this space, given the little time I have to talk about it. So there is some early work by Bruch and other people, and people have built Bayesian graphical models, and there's a system called Prox. If you've used Eclipse, you will see, you might have used this system. But how do you evaluate the goodness of these things? Is it number of keystrokes that the user that has to type? Have you reduced the number of keystrokes the user types? Or the overall productivity of the user? Or are there reduced bugs when users use your API versus the recommended API versus the default APIs? And so we have a ton of metrics to measure the goodness of one of these things. Okay? The other thing we can do is that, can we infer code conventions from the software, from the code, right? So code conventions are good for better maintenance. Or code formatting. Today we have linter rules, which are giant rules that get run when you're editing your code, and they're all rule-based. And the rule-based system, the typical problem is you have completeness issue, you also have correctness issues. Sometimes the rules are wrong because they're human typed. At other times, the rules are not complete. So you kind of have incomplete piece of work that is done. So there's a bunch of AI-driven work from our team related to variable naming, or how to better name variables, or how to, you might be misusing a variable. So for example, if you have an example of a first name, comma, last name, some people, they're both string types, but at the same time, if you pass in last name, comma, first name, the program is going to run wrong. How do you figure out those kinds of mistakes in your code? And there's a ton of work in that space as well. So the second thing, the next thing is like inferring bugs in your code. So, how do I figure out, is your code likely to be buggy, right? So buggy code kind of contains unusual patterns, and the probabilities of their occurrence are different from normal code. So there's a bunch of work that we've done in that space, and one of the problems here is that it's very hard to achieve high precision. So, but at the same time, if you can increase the recall and kind of say this is likely to be buggy, we found that to be very useful as well. And finally, this is kind of the nirvana of code generation, where can I automatically write code for you? So there's a ton of work in program synthesis that has been done over the last few years. So there is, I list a few pieces over there. There is a deep coder from MSR Cambridge. There's also the Prophet and Genesis work from MIT. And there's a Bayou system, Rice University, which basically you give an example, or let's say if you have a block of code, you write one line of code there, and it tries to write the code around it for you, right? The problem with many of these things are they work very well for curated data sets. When you actually try to put them into your system, they don't work very well at all. And the expectation from the programmers is very, very high, which means if you go wrong 1 out of 10 times, they hate it a lot more. If you make a recommender on Amazon, and if you're wrong about 5 out of 5 times, it's 5 out of 10 times, it's okay, because it's kind of, there's the cost of going wrong is much less, versus when a programmer is writing code and you recommend wrong code to them, the cost of being wrong is much higher over there. So we really want high precision systems, or at least if the system is of lower precision, we want to make sure that it is less interfering to the user. So there's a combination of using algorithms and experiences that we need to combine when we present it to the user. Okay? So I'm going to talk about one example, which is IntelliSense. And so IntelliSense is basically when you like this shows animation of different languages, C#, C++, Java, XAML, and Python. And it says, a lot of the code you write is something dot, and you may want to make a function call. So what should that function call be at any point of time? And standard recommenders give you an alphabetical list of recommendations. Can we do better than that? Very simple problem, and at the same time, what we found was it is very, very useful when we make a better recommendation. And if you make a wrong recommendation, it is very annoying to the user. Okay? So the learning dilemma for us was we had a bunch of people who had deep learning approaches, and we had a bunch of people who had cheap learning approaches. So how do we make our algorithms really simple, but at the same time, they scale really well, versus something that's very complex? So I'm going to give you both the examples. I'll start with cheap learning, which is doing very simple things and making your thing efficient. Okay? So here's, I'm going to walk through a set of examples. So I'm writing some socket code. So the part that's in green, let me point to that. The part that is in green is the one that's commented out, and what we want, the recommendation should match that. So I comment that out so that I see what kind of recommendations are there. So for example, if I type in s.socket, the recommendation should be a socket call, right? And that's kind of what it is doing over there. And then after that, there's a parameter to be passed, and then that socket.afinet is what is to be recommended. And then I follow that. Then I got another line, which is I created the socket object. Then I need to make a call, and the call should be to connect. So instead of going alphabetical, if the system can make the system can make a recommendation of connect, then I know that I need to do a connect call, right? And then follow that, I need to send a message over the socket, and after that, I need to do a receive, and so it makes a receive recommendation, and And so these are the sequence of recommendations it should make. So even though it's an invocation on the same object, the recommendation changes as you start writing code, and that's kind of that's the ideal situation. So can we get as close to this as possible? So now the recommender has to have context of what you've written, what you're writing, what does the rest of the code look like, and make the best job it can do, right? So let's take a data-driven approach. So what we have here is, we have about 2,000 plus C# repositories, and out of which we had to clean, we had to build the systems because we had to build the entire graphs or the trees out of those repos. So we could build about 700 of those, and we found about 200,000 C# documents in our data set. Then we ask a lot of questions of the data set. So what are the most frequently used classes? Are there patterns in how these methods in one class are used? And what are the features that are useful? So when you're making a prediction, what pieces of information provided by the analyzer would be useful? What is a reasonable segment of code to look at? Should I look at the entire function? Should I look at the 5 previous lines? Should I look at only the current line? Should I do any kind of interprocedural analysis? And stuff like that. And how do we make the recommendations? So will the same model work across all classes, across all functions, across all libraries, etc.? Do I have enough data? So these are all the questions that when you have data, we have the questions that we need to answer. So one thing is here, the first thing to do is to say, hey, let's look at all the invocations in all of the repos that we saw. And what we see here is that, as you would expect, a long tail, right? So if you look at the invocation graph of the top 50 classes there, right? They cover about, top 100 classes cover about 28% of our code. So if I can do well for the top 100 classes, then I get about 30% coverage. That's pretty good, right? And most classes are like string classes and control classes and so on and so forth. And if I do well for those classes, then I get my coverage very well, and I also get my precision. So I don't have to do really well for all the classes, the most commonly used classes. If I do well, then I'm good enough. And that's what data tells me, and that's a good insight into what I should be doing. Then I ask the question, how often is the first invocation happen? So we saw that in the first one, socket dot, the first call to socket. How often does the first call happen? Because when the first call happens, I have no context of how it is going to get used. And if you look at the top 100 classes, we find that about 14% of the top 100 classes have first invocation. And then about 64% of the classes have fifth or so invocation. So I know the cold start problem is about a 14% problem. because the first invocation is a hard one to predict. And once I know the first one, the second one is easier, the third one is even more easier, and so on and so forth. So if you look, same thing I do with the top 100, 200, 300 classes, and as I go to more classes, I have more cold start problems. So that is something I need to keep in the back of my mind, right? So based on this, we kind of said, well, looks like we need a sequence model. And the sequence model is something that understands how method calls are made within a piece of code. So if you look at this code, you got, if you look at this piece of code, there's something related to text, and then I make a call text.greater than 1, token.string, token.toLower are these two token method calls, and I want to make a prediction over here as to what should I do now. So I have a context of these two classes. Will these two things tell me what I should invoke over here, right? So, and what we did, long story short here, we ran Markov chains of different lengths, length 1, length 2, length 3, length 4. At some point of time, you're going to have diminished returns, and as you have longer and longer chains, your model sizes are going to get bigger and bigger. And what we found is just having context of about 2 calls behind, we can do really well. We can get an accuracy of about 60%. So with that, we found that this could perform really well in the offline environment, and then we could ship it for online testing. So I'm going to show you just 2 examples here. So the frequency model is one of the things that you often find in IDEs, where I will recommend the most commonly used call. And so this is kind of what you see on the left-hand side. The model size is pretty small. It is only a 1 megabyte model size. When you use a sequence model, it becomes about 5 times as much bigger, but the accuracy goes up about 40%. So here you get an accuracy of about 38. Here you get an accuracy of about 58%. So and constantly when we deploy this in production, we have to trade-off between model accuracy and model size and the time it takes to deliver the model. So these are the 3 things we constantly look before it is accepted to go into production. So this was one track saying, hey, we have simple models will give you something, but at the same time, as you go and scale it to many more packages, many more languages, many more classes, the challenges become bigger and bigger. So we will talk about the second part of this approach using deep learning in a minute. But today, this model is deployed across many languages, C# and Python, and C++, Java, XAML, and TypeScript. And it is, if you use VS Code for code generation, for your development, then this intelligent system is available to you. Now, the second part of it is to use the deep learning approach. So the deep learning approach, what do? I take my code, and I have created a representation. I create an embedding of that code. So I take the AST and serialize the AST, then I vectorize it, and I create an embedding. Then I have a neural network architecture. In this case, it's a fairly straightforward standardized architecture that you see. It's a two-level LSTM and two-layer LSTM with 100 hidden units, and then a bunch of stuff. You can read the details in the paper because I'm running out of time here, so I'm trying to finish it here. But the main point is this is fairly complex, and it gives us much better accuracy, but at what cost? So we had to learn a bunch of hyperparameters here, and we searched the hyperparameter space and figure out what the learning rate should be and what type of RNN we should use, what's a batch set we should use. We had to do distributed training offline, and so what kind of batching we should do. Then to run it on the edge, we needed to reduce the model size, so we had to do a bunch of quantization and go from floating point to word size and so on and so forth. All the details are in the paper. But after doing this, we get a pretty good accuracy. So we go from, let me go back to that slide of accuracy. So if you were to compare all of these things, we go from what we would have got with a 58% accuracy to a 71% accuracy. So it's much better when we use deep learning. But at the same time, what cost does it come at, right? So, right? So one of the and the second problem here is also, the model is much bigger. In the next slide, I'll show you how big the model is, right? So the model is about 5 times bigger than the model that we had deployed before, with almost no accuracy loss. And we've done a bunch of optimizations at the last layer as well, but still, it is quite big. Now, in the model compression, we could reduce the model by a fifth, but at a very low accuracy loss. But still, our serving speed is about 5 times slower than what it was on the edge, which is not acceptable. So if you're typing your code, if it takes 50 milliseconds for it to come back with a recommendation, that's not going to be acceptable. So there's a ton of work to be done in this. But on the other hand, it is promising what it is achieving here. Okay, so I'm going to skip over this because I'm out of time. So it is in my slides, which talks about how to teach machines to review code. I'm not going to be able to talk about that. I'm going to run to the last slide, which basically says, we have huge opportunities in automating parts of code generation, parts of how to write, recommending codes, etc. Because we have lots of data, and we see advances. So for example, this was standard, well-architected neural network model. We can use transform networks to do much better than what we do today. But at the same time, we have challenges as well. The challenges being how well it performs on the edge and how quickly it comes back. If you want a model running on the client, which is even your desktop, I cannot afford a 250 megabyte model just to make a method recommendation. So how do we make these models run efficiently on the client? So we barely scratch the surface, but at the same time, I think we have huge opportunities to make big dents here in the future. So the whole space of using AI for software engineering is pretty nascent, and there are big opportunities there. And I hope you get, if anything you get away from this is like saying, okay, this is new kind of data, this is not image data, this is not video data, this is not LNP data, this is really code data, and what can we do here to use AI to make things, automate things, and help the developer be more productive. With that, I want to stop, and I don't know if you have time for questions.
Let's have you answer those during the break.
Okay, great,
Thank you.